In this chapter, we will go over alkenes and cycloalkenes. So to start, organic compounds, these are compounds that are made up of carbon atoms. Normally, compounds that have carbons and hydrogens, we call them hydrocarbons. And organic chemistry is the study of these compounds. When we want to represent a carbon always have 4 single bonds. These single bonds, we call them sigma bonds. And each of these sigma bonds constitute 2 electrons. So in order for carbon to achieve octet, it needs to have 8 electrons in there. So we know that carbon has 4 valence electrons. This is a review of 111. So carbon has 4 valence electrons in there because carbon is a group number 4. And carbon makes a covalent bond with another 4 electrons to achieve the octet state. So let's say, for example, if I want to draw the Lewis structure for CH4, I know that carbon has 4 valence electrons, and I know that the hydrogen has 1 valence electron. I have 4 of those. So each of these hydrogens, each of the electrons of the hydrogen, it's going to bond with the electron of the carbon, and it's going to make a sigma bond. And this is why we said that a sigma bond constitutes 2 electrons in there. So to draw the Lewis structure of the CH4 in there, you have to draw all of these hydrogens in there, all of these hydrogens in there, and each of these bonds, they represent 2 electrons. Now, these bonds are considered to be covalent bonds. And covalent bonds are the most common bonds in organic compared to the ionic bonds. Now, carbons, nitrogens, and halogens, all of those, they follow the octet rule. What does that mean? It means that they need to reach a stable state, which is 8 electrons, so that their charge, their formal charge, is 0. So carbon reaches its formal charge state to be 0 whenever it has 4 valence electrons and it reacts with 4 more valence electrons in there, so that it reaches 8 electrons, so that it is octet. For nitrogen, nitrogen has 5 valence electrons, so it needs 3 more valence electrons in there. This means that it needs to do a sigma bond with 3 atoms in order for it to be 8 valence electrons. Oxygen has 6 valence electrons, so this means that it needs to bond with 2 groups in there, so it needs 2 more electrons in order again to reach 8 valence electrons. Same thing for halogens in there. So halogens, we know that they are group 7, so they have 7 valence electrons, so they need to bond with 1 more electron in there, meaning 1 more group, so that they can reach the 8 valence electrons. When all of these atoms, they reach their octet state, their formal charge is 0, and we say that they are stable. The rules that we follow whenever we want to draw a Lewis structure, the first thing you do is you need to calculate the valence electrons. And remember, valence electrons is equal to the group number. So you start by carbon. Carbon is group number 4, plus you do have hydrogen, which is group number 1, and you have 4 of those. So you have a total of 8 valence electrons. To draw the CH4, there are 2 ways to draw it, either by doing the Lewis dot structure or the Lewis bond line structure. I would prefer to draw the Lewis bond line structure, but we're going to go ahead and draw both of them. So the rule says that you choose the least electronegative element with the exception of hydrogen in there. Down there, I do have the electronegative table. So if you look at the hydrogen and the carbon, Carbon is more electronegative. This is the electronegativity value compared to the hydrogen there. But the rule says that the least electronegative element, with the exception of hydrogen, has to be in the center. So hydrogen can never be in the center. So this means that carbon is going to be in the center. So you go ahead and you put the carbon in the center there. I'm going to draw the Lewis dot structure. We know that carbon has 4 electrons because right now what I am doing is I am distributing the 8 valence electrons. So carbon has 4, and then the hydrogen there has also 4. You can draw it like this, or you can put the electrons above each other. It doesn't matter. So this is called a Lewis dot representation in there. And instead of drawing these 2 electrons like this, we can combine them in a single bond, which is a sigma bond, which I prefer. And this is called the Lewis bond line structure there. So that is going to be the CH4. This is going to be the Lewis bond line structure. Let's use this because during this course, we're not going to use the Lewis dot. We're going to use the Lewis bond line structure to represent organic compounds. Now, in order to determine the geometry, the shape of the molecule, this is a revision for 111. We're going to look at the VSEPR table. This table is found in your eCampus, so you can use that. Let's see where it is. Okay, here you go. So that is the VSEPR table in there. So with the VSEPR table, you're going to start by calculating the steric number. The steric number is the number of groups that are connected to the central plus the lone pair. Okay, so we're going to start over here by calculating the steric number of CH4. So steric number is equal to what? How many groups are there around the carbon? So we have 1, we have 2, we have 3, and we have 4 in there. So this means that it is 4 plus the lone pair. What does a lone pair mean? So right now we distributed 2 electrons each. So you have a 2 electron, a 2 electron, and over here you do have a 2 electron. So right now we distributed all the 8 electrons around the carbon. This is your valence electrons. Remember that the value of the valence electron need to be always even. So we distributed the 8 electrons. We don't have any other lone pair. If there is any left over from the 8, you go ahead and you put them on the central carbon. And this is called a lone pair. But there is none. So the lone pair here is going to be a 0. So the steric number here is equal to 4. So you go to the table in there. You go to the table and you look for steric number equal to 4 and lone pair equal to 0. And then the geometry is equal to the tetrahedral, and the molecular shape is equal to the tetrahedral as well. What's the difference between them? The difference between them, if there is any lone pair in the central atom, that lone pair will change the structure of the molecule, the shape of the molecule, and it's going to squish the bonds a little bit, so the bond angle will be less than that of the geometry. But for us, there is no lone pair for this example. So the molecular geometry and shape, they are the same. And this is how you draw them. This is called a tetrahedral carbon. A tetrahedral carbon is a carbon that has 4 groups around it, 4 different groups around it. So here you have your 4 different groups around it. And normally we represent a tetrahedral carbon by 2 bonds in plane, 1 bond behind, and the other one in front. This is called the wedge and the dash. So the dash represents the atom that is behind, and the wedge represents the atom that is in front. It's just pointing towards you. Okay, so you can draw it in any way you want, as long as every carbon has 2 bonds in plane, 1 bond which is going to be in front, and the other one is going to be behind. So I can show it like this. I can also show it like this, for example. So I have a hydrogen here, a hydrogen here, a hydrogen here, and then another hydrogen in there. It doesn't matter. Both of these are going to be the same. There are other representations because I can take this molecule and rotate it and view it at any angle in there. So, but make sure that every carbon has 2 bonds in plane, 1 bond in front here. So this bond is going to be the wedge one is going to be in front, and the dash one is going to be behind. And that represents a tetrahedral carbon. So this carbon over here is a tetrahedral carbon. The bond angle, normally you measure it between the lines that are in plane. So here I do have 2 lines that are in plane, so the bond angle is 109.5, and this is for the tetrahedral structure. So by looking at the VSEPR table, the geometry is going to be tetrahedral, and the shape is going to be tetrahedral as well. Okay, now once you go ahead and you put out the shape and the geometry, very important, now we're going to look at the polarity, and this is still a revision for 111. So for the polarity, to determine the polarity in here of any compound, you need to draw its VSEPR shape. So this is the VSEPR shape in there because the shape is the same as the geometry in this example. And then we are going to check the difference in the electronegativity between the atoms. So over here, we do have the carbon, we do have 2 hydrogens that are in plane, one in front and the other one is behind. If you don't draw the geometry or the shape, then in this case, your polarity is going to be wrong, okay? So now in order to determine if the molecule is polar or not, polarity means the movement of electrons. So we want to check if the electrons move or not. And to do this, we would need that electronegativity table in here. So with the electronegativity table, you look and see which element is the most electronegative element. And electronegativity normally increases from left to right in a period and from bottom to top in a group. So if I am comparing between carbon and hydrogen, carbon is more electronegative. But the difference in the electronegativity is really low because you take a look and see carbon is 2.5, hydrogen is 2.2. So this is very low. So the type of bond between them, if I want to determine the type of bond here, if hydrogen is 2.2 and carbon is 2.5, all what you need to do is just subtract the electronegativity values in absolute value. Okay, so it doesn't matter here if you do 2.2 minus 2.5 or 2.5 minus 2.2. And the answer here is going to be 0.3. So if you look here at this table, if the difference is less than 0.5, then I know that all the bonds are non-polar covalent bonds in there. So all of those are considered to be non-polar covalent bonds. Okay, so to determine now the polarity in there, which I said the movement of electrons. So you already know here that this is a non-polar covalent bond. So your molecule here has to be non-polar. So let's go ahead and prove that it is non-polar in there. So you look at the electronegativity, and the carbon is more electronegative than hydrogen, meaning that carbon is going to take electrons away from the hydrogen. Same thing here, carbon is going to take electrons away from the hydrogen. Carbon is going to take electrons away from the hydrogen, and it's going to take electrons away from the hydrogen. Notice that your arrows cancel out. So these two are going in the same direction of these two. So your arrows are going to cancel out. If your arrows cancel out, this means that there is no movement of electrons. So your dipole moment, we say that the dipole moment here is equal to 0. And your dipole moment is equal to 0, then your molecule is considered to be a non-polar. And because the bonds are covalent, we're going to call it a non-polar covalent molecule in there. Let's continue with more examples. Ammonia, NH3. Ammonia is used as a solvent and it is used as a base. So we're going to calculate the valence electrons for ammonia. Nitrogen is group number 5 And hydrogen is group number 1. I have 3 of those, so that is 8 valence electrons. Please pay attention that the valence electrons have to be even. It cannot be odd for these organic and inorganic molecules in there. Of course, there are exceptions, but we are not talking about exceptions in this course. So now we want to distribute the 8 valence electrons. You go by the least electronegative element being in the center with the exception of hydrogen, or you go by the unique element being in the center. So nitrogen is a unique element, meaning that it is the only element which is nitrogen in the NH3 molecule. So this is why nitrogen is in the center in there. And connected to the nitrogen, I have the 3 hydrogens. So I put the 3 hydrogens like this. Okay, so far I've used 6 electrons, so I still have 2 more. Whatever is left, you just put it on the ammonia, and that is going to be the lone pair. So how many lone pairs I have? I do have 1 lone pair. To calculate the steric number, it's the number of atoms connected to the center. So here I do have 4 of them, or 3 of them. And plus the lone pair, so it's the number of atoms connected to the center, which is 3 of them, plus the lone pair, which is 1. So the steric number here is equal to 4. So I go to the table in there. So here you go. I go to the VSEPR table, and I am looking for steric number of 4, and I am looking for a lone pair of 1. The geometry is a tetrahedral, but since I have a lone pair, then the geometry is going to be different than the molecular shape in there. So the shape here is going to look like a trigonal pyramidal. And notice like the presence of the lone pairs, what did it do to the bonds? And then it squished the bonds. So the bond angle now is going to be less than the ideal bond angle, which is the 109.5, because it's still tetrahedral. So the bond angle is going to be 109.5, but because of the presence of these lone pairs, they need room, so they're going to squish the bonds. And this is how you represent it in there. This table, you're going to have it in the exam, so you can bring it in the exam. So I know that the geometry is going to be tetrahedral, and the shape is going to be a trigonal, pyramidal. And when you want to draw the trigonal pyramidal, always you put your central atom in there, and then you do have one atom which is in plane. Here I'm just going to make any of the hydrogens in plane. The other one is going to be in front, and then the other one is going to be behind. And you do have your lone pair as well. Your lone pair is also going to be in plane. So these two are going to be in plane in there. And the bond angle in this case, so the bond angle between these two lines in there is going to be less than 109.5. Okay. So now when I want to check the polarity of the molecule after you draw your molecular shape, so this is the shape. So after you draw the shape, now we're going to check the polarity of the molecule. To check the polarity of the molecule, go with the electronegativity, use the electronegativity table. Nitrogen is more electronegative than hydrogen. Remember that electronegativity increases from left to right in a period, bottom to top in a group. And you will have your periodic table with you in the exam, and you will have all of these electronegativity tables and the rules in there. So between nitrogen and the hydrogen, nitrogen is more electronegative. It's a 3. It's more electronegative. So nitrogen will pull electrons towards it. Same thing. And same thing over here. This is called the path of the electron, which we call it a direction of polarization. It shows how the electrons are pulled to the central atom. And there, the arrows, they don't cancel out. So if they don't cancel out, then the dipole moment is going to be different than 0. And if it's different than 0 in this case, then we're going to call this a polar covalent. You can also do the difference in the electronegativity, and you're going to reach the same conclusion in there. For the NH3+, we're going to do the same thing, and we're going to calculate the valence electrons in there. Nitrogen is group number 5, hydrogen group number 1. I have 4 of those. Now the plus charge. The plus charge is the charge of the whole molecule in there. Okay, but because nitrogen is the central atom, then that positive is going to belong to the nitrogen, not to the hydrogen, to the nitrogen in there. So every time you have a positive charge, you would need to go ahead. Positive means that you are actually losing electron. So if you're losing electron, you need to show that you are losing electron in this case. So this is going to be -1. If it was +2, then you are going to lose 2 electrons in there. And that is going to be an 8 valence electrons. Again, always double check your answer. Your answer has to be even number of electrons in there. We're going to go ahead and draw the valence electron or the Lewis structure in there, the Lewis line structure. So that is the Lewis line structure. Notice the difference between the Lewis line structure and the geometry and the shape of the molecule in there. You always need your molecule. You start with the Lewis structure always and change that into a molecular shape so that to determine the polarity. My charge always in the Lewis structure, so this is going to be the Lewis line structure. Always in the Lewis structure, you put your charges. So here the nitrogen is going to be positive +1 charge. This is a formal charge calculation in there. This is the equation for the formal charge, and this is the table for the formal charge. And this is supposed again to be a revision for 111. So when nitrogen has 4 bonds, it should have a +1 charge. You can either go with this table or you can go ahead and put the values in here and get the formal charge. You're going to get the same answer, which is +1. So the number of electrons, if I want to go with this formula in here, the number of the valence electrons in the free atom, which is 5, because I'm calculating the charge of the nitrogen, -½ my bonding electrons. The bonding electrons are the electrons around the nitrogen, and this is 1, 2, 3, 4, 5, 6, 7, 8. Notice that it says electrons, so I have to count all the electrons in there, not the bonds. So that is going to be 8 minus the non-bonding, which is 0. So that is going to be 5 minus 4, and that is going to be a +1. This is why the charge of the nitrogen is +1. But it's always faster and easier to go with this table in here rather than putting all of these values and wasting time in the exam. So we're going to calculate the static number in there. So the static number here is going to be number of atoms connected to the central, and I do have 4 of them. I don't have any lone pairs, so that is going to be static number 4. The lone pair is going to be 0. Look at the table, at the valence, at the VSEPR table, and the geometry will be tetrahedral, and the shape will be tetrahedral as well. So I'm just going to draw it as a regular tetrahedral in there, and then go ahead and find the polarity. Okay. For the polarity in here, nitrogen is more electronegative than the hydrogen. Same thing, nitrogen more electronegative than the hydrogen, more electronegative and more electronegative as well. So you can easily see that your arrows over here, they do cancel out in there. So these two and these two, they go into the same direction. So the dipole moment in here, it's going to be equal to 0. So your molecule is going to be a non-polar covalent. Okay, we know that all of these bonds are covalent bonds, and by definition, a covalent bond is a bond that is formed between 2 nonmetals. Nitrogen is a nonmetal and hydrogen is a nonmetal. Always hydrogens, they do form covalent bonds. Of course, there are exceptions, but we are not going to talk about exceptions in this course. Another example, H2CO. H2CO is considered to be the molecular formula in there. So same question, go ahead and find its molecular geometry and shape and determine if the molecule is polar or not. So let's go ahead and find the valence electrons in there. Valence electrons are, for the hydrogen, I have 2 of them, and then the carbon is going to be 4, and then the oxygen is going to be 6. And that is going to be a 12 valence electron. Again, it is even. So I always look at the lowest electronegative element with the exception of hydrogen. So between carbon and oxygen, carbon is less electronegative than oxygen, so always carbon is going to be in the center and not the oxygen. Remember, when you're putting this structure together, that carbon needs 4 bonds. Carbon needs 4 bonds because carbon is always stable in its zero formal charge. If it has 3 bonds, then it's going to be +1. If it has 3 bonds and the lone pair, it's going to be negative. And the charge of this guy is 0. So carbon has to have 4 bonds in there. So I'm going to start by adding all of these atoms around the carbon. So I'm going to start with the hydrogen in there, the hydrogen in there, and then the oxygen here. I can put the oxygen on top. I can put it here at the bottom. It really does not matter. Right now I used 6. I still have 6 in there. To have 6 in there, you forget about the central atom. You would need all the atoms around the carbon to be octet with the exception of the hydrogen. Hydrogen can never be octet because hydrogen forms a covalent bond. It has 1 electron because it's a group number 1, and it shares another electron with the carbon. So hydrogen can never be octet, but the others are. So oxygen there has to be octet. Right now oxygen has 2 electrons. It needs 6 more. So that is going to be 1, 2, 3, 4, 5, 6, and that is going to be a total of 12 electrons. But I have a problem there because carbon is not octet. Carbon has 6 electrons right now. So what I need to do every time I have a carbon-oxygen situation, I normally take 2 electrons from the oxygen and they create what I call a double bond in there. So in this case, I satisfy the octet rule for both, for the carbon and for the oxygen in there. You can keep those lone pairs like this, or you can move them on the side. On the side they look better, so I'm just going to move them on the side. So right now this is going to be my Lewis line structure. Every single atom that I have is octet. Oxygen has 2 bonds, 2 lone pairs, and when oxygen has 2 bonds and 2 lone pairs, its charge is 0. Carbon has 4 bonds in there, so this is 1, 2, 3, and 4. So its charge is 0 over here, so I am set. Go ahead and calculate the static number, which is the number of atoms connected to the central. The central is the carbon, so the number of atoms that are connected to the central is 1, 2, and 3. So that is going to be 3. There is no lone pairs around the carbon, so that is going to be 0. So I know that the static number is 3. Look at the Vosper table, and then the shape and the geometry, both of them. So the geometry and the shape both are going to be trigonal planar. Okay. And to draw a trigonal planar, if you look at the table in there, this is how you draw the trigonal planar. All the atoms, they lie in the same plane. So you don't have a wedge in the dash here. Just all of them, they lie in the same plane, and the bond angle between them is 120 degrees. So to draw it, I'm just going to go ahead and draw it like this. I'm going to make an angle, and I'm going to make another angle in there, so that the angle between each of these is 120 degrees. Put the lone pairs, and now we're going to determine if the molecule is polar or not. So check the direction of polarization. Carbon is more electronegative than hydrogen, carbon is more electronegative than hydrogen, and oxygen is more electronegative than any. So notice that the pull of electron is not canceling out. It's going all the way towards the oxygen, because oxygen is the most electronegative in there. Since it's not canceling out, we would say that the dipole moment is different than 0. And this means that the molecule is going to be a polar covalent molecule. Okay, there's a difference between a polar covalent bond and a polar covalent molecule. So the molecule as a whole is going to be a polar covalent. But notice that the carbon hydrogen, these two are a non-polar covalent bond. Okay, so there's a difference in there. So my dipole moment here is going to be different than 0, and we would say that the molecule is going to be a polar covalent molecule because it contains that carbonyl. It's called a carbonyl, a carbon double bond O in there. And this is the source of the polarity. This is what makes the molecule polar in there because of the oxygen, and the oxygen pulling the electrons away from the carbons and from the carbon and from the hydrogen. When you have a molecular formula that has more than one carbon, all carbons, they have to be connected to each other. So you connect the carbons to each other as a carbon chain, and carbons, they can make either a single bond, they can make a double bond, and they can make a triple bond in there. So we're going to vary their nomenclature. We're going to name them different. So if they make a single bond, we call them alkanes. If they make a double, we call them alkenes. And then if they make a triple bond, we call them alkynes. Now, alkanes, since they don't have any double bonds in them, we call them saturated. So saturated is a term that we use for a hydrocarbon chain that does not contain any double bonds in there. And alkenes, they follow the formula CnH2n plus 2, where n is the number of carbons. For alkenes in there, these are unsaturated. Same thing for the alkynes. So alkenes and alkynes, these are considered to be unsaturated. Unsaturated means that they do have a double bond and a triple bond in them. Alkenes have a molecular formula of a CnH2n, and this is how you can differentiate. If I give you the molecular formula, you can simply relate it to any of those and know if you're working with an alkane, alkene, or alkyne. Alkyne is a CnH2n negative 2 in there. Okay, you are required to know those. So this is the difference between saturated hydrocarbons and unsaturated hydrocarbons. Just keep in mind that every time you are given a molecular formula, you need to know if the formula follows any one of those so that you can relate to what hydrocarbon structure that is. Now, another way to know if our structure contains double bonds or cycles in them, and we will talk about cycles as we proceed, is to calculate what we know as the DBE. DBE is the double bond equivalence, and this one is going to tell us the number of double bonds or the number of cycles that we have in our structure. It's a simple formula in there. There are multiple formulas in the books. I use this one. You are free to use whatever you want. And you don't have to memorize this. This one also is included in the sheet of tables that you can bring in to the exam. If your molecular formula has oxygen, sulfur, and phosphorus, just go ahead and neglect it. If it has a group number, any of group number 7, which we call them halogens, then you're going to add them to the number of hydrogens. So let's say if your formula has 2 halogens in there, 2 chlorines, for example, and 6 hydrogens, just add them together. And 6 plus 2, that is going to be 8, so that is going to be 8 there. The number of nitrogens, if there's any nitrogen in your formula, you subtract it from the total number of hydrogens. The value of the DBE is always an integer, so it cannot be a decimal. And it can range from 0 until X number in there. It's going to be 0, 1, 2, and 3. So if the DBE is 0, then we are talking about alkanes. So for alkanes, the DBE is equal to 0. Why? Because alkanes, they have no double bonds in there. They have no cycle in them. For alkenes in there, normally the DBE is equal to 1, depending on how many double bonds we have. Every double bond is a DBE of 1, okay? And every triple bond for alkynes is a DBE of 2. So a triple bond, this is called a triple bond. A triple bond is a DBE of 2. A double bond is a DBE of 1. And a cycle is a DBE of 1. Let's go ahead and draw the Lewis structure. These are examples of more than one carbon. In there, as I said, you would need to determine the valence electrons for each one of them in there. Now, You can make it easier than this. You can skip the valence electrons since you don't have any oxygen in here. You can skip the valence electrons. And you can go ahead and go by the rule by connecting the carbons together. And every carbon needs to have 4 bonds in there. So what I have here is, this is a C2H6. So I am left with 3 bonds here for this carbon to be octet. I'm going to fill those with hydrogens. And I am left with 3 bonds here for this carbon to be octet. So I'm just going to fill those with hydrogens in there. If you calculate the valence electrons of C2H6, if you count the electrons here, you're going to see that they are the same. But it's just like you're skipping that step of the valence electrons because no need in there. But the whole idea is whenever you have more than one carbon, you need to connect the carbons together and make sure that every carbon has 4 bonds in it. Okay, C2H6 follows the formula CnH2n plus 2 in there, where n is equal to 2 in this example. So that this means that the DBE is equal to 0, and I have no double bonds or cycle in my structure, so definitely I am working with an alkane, and alkane is all single bonds. Now, C2H4, and this is the importance in there of relating the molecular formula in order to draw the Lewis structure, because C2H4 follows the CnH2n molecular formula. And the CnH2n, I know that this one is going to be an alkene in there, because if I go ahead and I work the DBE for this molecule, it's going to be the number of carbons, which is 2, times its number of carbons times 2 plus 2 minus the number of hydrogens divided by 2 in there. So that is going to be 2 divided by 2. This is going to be equal to 1. DBE of 1 in there, that is going to be 1 double bond. So I have here 1 double bond. Okay, I can also have a cycle. We will talk about this as we proceed. But right now, this is the molecular formula that follows the alkene in there. So I do have a double bond. Let's go ahead and draw the Lewis structure for this one. Again, connect the carbons together. Right now, I've used two bonds for each of the carbons. I still have 2 more. So I will have a hydrogen here, a hydrogen there, a hydrogen here, and the hydrogen there. If you look at the molecular shape for each one of these carbons, since this carbon has 3 groups around it, it needs to be trigonal, planar, geometry, and shape. So this is why when I am drawing it, I am drawing it as a bond angle here of 120 degrees. This one is 120 degrees because each of these carbons in there is going to be a trigonal, planar, geometry, and shape. So each one of them is a trigonal, planar, geometry, and shape. Now for the C2H2, this is going to follow the molecular formula CnH2n minus 2, which is an alkyne in this case. So if I go ahead and do the DBE for it, that needs to be equal to 2. So the number of carbons times 2 plus 2 minus the number of hydrogens divided by 2, and that is equal to 2. And the DBE of 2 is equal to a triple bond in there. So if I want to draw its Lewis structure, again, no need for you to calculate the valence electrons in here because I know I only have 2 carbons. So I'm just going to go ahead and draw the 2 carbons. I'm going to draw the 2 hydrogens in here. I know that every single carbon has 4 bonds in there. So this means that I would need to put these triple bonds there so that I would end up getting, for every carbon, 4 bonds. I cannot make a double or a triple between the hydrogen and the carbon. Remember, hydrogen always makes a single bond in there. A triple bond is a linear molecular shape and a geometry. This is 180 degrees, and that is supposed to be a linear shape and geometry.